We're talking about train engines today and all the physics for heat engines. Channel your inner engineer. We're going for a ride on the train, the physics train. So we're studying thermodynamics for this. And thermodynamics is the study of processes which we transfer energy as either heat or work. Heat is when we have a change in temperature that changes our energy. Work is when we have a change in energy that does not produce a temperature difference. Now, just because something comes in as a heat energy doesn't mean it goes out. We can transfer things from one of those to the other one. So like Q is the heat energy added, but it doesn't always just change the temperature. Sometimes that heat energy added does work, and so it doesn't always change temperature, but it starts as heat energy. Let's go through the laws of thermodynamics. We've already done one of them. This first one, the first law of thermodynamics, we already talked about. Delta U equals Q plus W. Realize that that's just an application of the law of conservation of energy. Whatever energy goes in has to equal the energy going out. It can be changed forms, and that's essentially what the first law says. Our second law, and these laws are going to get a little fuzzy. The second law says heat can flow from a hot to a cold, but it cannot go from a cold to a hot unless you add some work. Like unless you do something to make that happen, it's not going to happen on its own. Another way to say that is it's impossible to transfer all your heat to work. You can't ever get rid of all the heat energy. There will always be some heat energy there. Another way of saying that, and the second law you say in lots of different ways, is that entropy increases. And that brings up what is entropy. So let's talk a little about that later. But right now, we're going to talk about the rest of the laws. We have a third law. Third law is kind of a corollary from the second one. It's saying it's impossible to ever reach 0 degrees Kelvin. 0 degree Kelvin is called absolute zero, and we cannot get something to that temperature because any process that we would use to try to get it there would add some heat to the system and keep it from getting to absolute zero. It's just a law that we can't get there, and that allows us to realize some things about heat later on, and so it's important enough to make a law out of it. After we did 3 laws of thermodynamics, they realized that there needed to be another one, and the person that invented that got to name it, and they had a little sense of humor, and so they said, we're going to make it the zeroth law. So we didn't make a 4th law, we said zeroth, and the zeroth, it was supposed to mean that it came before all the other ones, so that's why we made it zeroth, but really it's just, I think, to be funny. But and it's to say that if 2 systems are in thermal equilibrium with each other, one is in equilibrium with the third system, then the second system is in equilibrium with the third as well. Essentially that's saying if A equals B and A equals C, then B equals C. Seems pretty obvious, but later on in thermodynamics, past what we do, this becomes pretty important, and so they wanted to make a law out of it. Essentially, we don't really use these laws too much except for this first one. Second and third, occasionally they'll have concept questions on. Really, we don't do anything with the 0th law, but I thought you should know about it because you hear about it occasionally, and I want you to know what it is. Back to entropy. Entropy is essentially a measurement of the disorder of the universe. So if you have a bunch of objects here and no objects here, that's a lot of order. If they're mixed up, that's a lot of disorder. And essentially, thermodynamics says that it always increases or remains the same. It can never decrease. So whatever processes happen spontaneously will always increase the disorder of the universe. It never makes the order more ordered. Now you can make small pockets of order, but to make those small pockets of order, you have to make bigger pockets of disorder around them. So, you can take a refrigerator, and essentially when you refrigerate something, you're making a pocket of order. You're making less heat in one place and more heat other places. But to do that, you have to heat up your entire house. Did you know you heated up your house whenever you're running your refrigerator? You do. And so you disorder a lot more than you are ordering. Okay? And so another way of saying this entropy thing is natural processes move towards a state of greater disorder. In any natural process, some energy becomes unavailable. So disorder means that we have heat that's not available. That's the whole friction thing. When we get friction, we end up with waste heat. We heat up the table or whatever, but we can't use that heat to run another engine. Essentially, to run an engine, we have to have a hot place and a cold place, and we'll get to that in a second. If we have a hot place and a cold place, we can use the difference in heat between those two to run an engine, to make a car go, to lift some weights, do whatever. But after we're done running it, we end up with a bunch of warm. Warm is disordered. A pocket of hot and a pocket of cold is ordered. So that leads to this weird heat death thing. When the universe was created, we had one tiny, tiny pocket of absolutely hot stuff, and then we had the whole rest of everything that was at really, 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 really cold, almost zero. We know it can't be exactly zero, but it's almost zero. So we had a lot of order in the universe. As it exploded outwards, the heat expanded out, and it was not as concentrated, it was less ordered. And so we get a lot of different stars around the galaxy now, or around the universe. A lot of galaxies around the universe, a lot of stars in the galaxy. And so now we have a bunch of stars. Now, stars are really, really hot, and all the space around them is really, really cold. And so we can use that to do things. The heat from the sun goes out to our planet, heats up our planet. That heat going that way is what allows us to survive. It allows plants to make photosynthesize to get sugars, and then we eat it. It's all due to the fact that there's some order here. But as our sun gets older and older, it gets less and less hot, and we end up with a bunch of warm. Now, eventually, in the entire universe, we're going to end up with less and less suns, more and more warm across the whole galaxy. Now, because there's so much empty space, the heat of everything, when it all gets to warm, is going to be still pretty cold. But once we get to that point and it's all warm, no one will be able to do anything anymore because there won't be any hot and cold. We won't be able to run any engines. You won't be able to go anywhere. That's what's called the heat death of the universe. And when the thermodynamics people had figured out that that was the eventual end of our universe, they told everybody and they named it heat death, which was a terrible idea, of course, because we call something heat death, people get depressed. They published their papers, and the number of suicides skyrocketed right then because we are a weird species. When we hear death in anything, we think, we got to kill ourselves. I don't know what the deal is. Another thing is that it's called sometimes time's arrow because as time goes on, there's more and more entropy. And so you can tell whether time is going forwards or backwards. It's always going forwards by how much entropy there is in a system. And so sometimes you use that to do some kind of problems to figure out which way a system will actually flow, because it always got to flow with more entropy, not the other way around. It's kind of weird things. For our purposes, conceptually, you need to know that it always increases or remains the same. Oh, also, on entropy. Since entropy is dependent on the state of the system, if I go from A to B to C to D and then back to A, since I'm coming back the same P and V, it ends up the same. Entropy would be 0 for that whole process. If it's cyclical, we always get an entropy that is constant, and that's something you have to know for some problems. Before we go into tackle heat engines, let's talk about a couple quick throw-in formulas that we have for this thermodynamic stuff. Heat flow is when you have some bar of a metal and you have a hot area here and a cold area there. And you want to know how fast the heat energy will travel from the hot to the cold. And there's a constant based on what substance you're doing, that's K. A is the cross-sectional area, so like that would be a square in that one. Length is the whole length of the bar, so the bigger your L, the longer it takes. The bigger cross-sectional area, the less time it takes. And then delta T is the difference in temperature from T2 and T1, the hot and the cold thing. So if they're really, really different temperature-wise, it'll happen faster than if they're not. Pretty easy equation, and really you just apply it, and really there's not a lot of hard stuff in that. You just apply it to that equation. Our other little easy equation is thermal expansion. It turns out that since heat is the jiggling of atoms in a solid, if you have a solid and you increase its temperature, since they're jiggling, it gets a little bit longer. And so the amount that it changes is a constant, coefficient of linear expansion, times the original length times the change in temperature, and it's pretty much a straightforward thing. Occasionally they'll have you do it in 2 dimensions, so they'll give you a big thing like this and find out what the change in L is there, find out what the change in L is there, and then find out what the change in area is. That would just be, the 2 L's multiplied together. And you could also do it for volume. Just do each side separately, length times width times height, and you can figure out how much the volume expands. But they're pretty easy equations, these. And just realize that just apply this. And that this is a delta. This is not the whole length. It's just how much it goes up by. The last steal it from your son snack. I cannot buy Doritos, but I have a really soft spot in my heart for them. I know they're awful for you. MSG, why is it so good? I don't know. It's made from seaweed. Seaweed does not seem like it would make you want to eat things so much, but it is. I do not buy Doritos, but my son loves them. And I know why. It's a genetic thing. I love them. He had a birthday a little while back, and he made us buy every type of Doritos there was for his birthday so he could try every single one. And I complained about it to him, and I said that's so unhealthy. We let him get whatever he wants for his birthday to eat. So we got them, but I was super happy that he did it so I could try them all. And here's my last confession about Doritos. When I was in high school, my mom went back to college, and so she would do things like leave some money for us to get dinner. We'd walk down to the local grocery store. I would buy the biggest bag of Doritos, about twice as big as this, and I would buy a 3-liter thing of Mountain Dew, and that would be my dinner when she left money for me. This is 11 ounces. It was like 30 ounces of Doritos and the giant fluorescent horrible. Oh my goodness, it was so amazing. And so occasionally, when my son gets them, I will eat them from him. And in honor of that eating, I'm going to eat them as my snack today. So, we got a heat engine. This is another visualization of a heat engine. Not on a PV graph, but just how it works. I said before, we have a hot reservoir and a cold reservoir. And to get an engine to work, we take some heat, that Q, that same heat added, we put it in the engine. We get some work out of the engine. Whatever's left over comes out as QC. We can't ever get anything to absolute zero, so there's no way we can get all of the heat energy to go into the work. We always have to have some waste heat coming out. That goes into the cold reservoir. The difference in temperature between those two tells us how good our engine can be. Okay? So this is the essential picture of what an engine does. Energy out there, does some work, whatever's left over gets put out. And so for internal combustion, I explode some gas, I get some work out of that gas, whatever's left over is the QC. I pump that out of my thing, and then I put some more gasoline in a spark plug, and I shoot it again. I get some more QC, QH. Some goes into work, some goes into C. And so that means that QC is equal to the work plus, QH equals work plus QC. This is what goes in. Some of it is turned into work. Some of it gets expelled as waste heat. And so the work is QC minus Q cold. And notice that a lot of times with these, we don't just want the energies, we want powers. And so power is work over time, and so the power is equal to QC divided by time minus, QH divided by time minus QC divided by time. So occasionally we use powers, so the rates instead of just the numbers. Right? That's how a heat engine works. So I said before, when we have our PV graphs, and I'm going around clockwise, that's an engine, that's this one here. This is our PV version of that. Our little diagram version of that is I take some heat from the engine, it goes into my engine, which is the little dot here. I get some work out, I have some waste heat that goes into the cold part, that is an engine. Remember, on a PV graph, a refrigerator goes counterclockwise. And my graph thing means I take something that's already cold, the refrigerator, take more heat out of it, make it colder by putting work in, and then I put a bunch of waste heat out into my room, thus increasing the entropy and making it very, very hot in your house. Okay, efficiency is measured as what you get out, the work, divided by what you put in, the QH. Remember, work is QH divided minus QC, and so a lot of times we'll use this one. Use one of these two equations most often, but some of the books will take and separate this out. QH over QH minus QC over QH, 1 minus QC over H. Sometimes they'll do this. But essentially, this is just figuring out how efficient my engine is. I know my efficient can't be perfectly efficient, because I'm never going to get all of my QC going into work. And it's nice to know how efficient it is. And they'll tell you that an engine is so much efficient, and then you have to figure out how much work you get out of it based on what you put in. So this is an equation we use often. Along with that equation, we have an efficiency equation that's of a Carnot engine. Now, a Carnot engine is the most efficient engine possible. It turns out that the most efficient engine possible can run forwards or backwards. So you need to watch out for that in concept questions. You need to watch out for Carnot engine in concept questions. And it turns out that to make the most efficient engine possible, you want a big difference between the temperature of the hot and the temperature of the cold. The equation is very similar to the regular efficiency one, except we don't use Q's, we use temperature. So it's not how much energy you get out, it's the temperature that it starts at and it ends up at. So you TH minus TC over TH instead of QH minus QC over QH. So this tells us the most efficient engine. So there's often times where you'll take this efficiency and they'll say if you have the most efficient engine, how much work do you get out of the engine? So you can take this and plug it into the earlier efficiency engine equation and figure out how much work you get out. Now it turns out that to get that most efficient engine possible, we have to have a 4-cycle engine. We start at A, we go to B, C, D, and then back to A. And 2 sides of that are isothermal, and so they're 1 over x functions, the top and the bottom, the red ones. And 2 of them are adiabatic, the 2 blue ones going up and down. That's the way we get the most efficient engine possible. And we'll watch a little video in class actually that shows why that is. A little bit about Carnot in general, but be ready to recognize this graph on a PV graph. When we have 4 sides that are all kind of curvy like that, looks kind of funky, you know that that's my Carnot efficiency, and realize that since adiabatic ones, the blue ones, have no Q in and out, this fits into my graph in that when I have this one here at the top, I have QH going in at the top, and I have QC going out at the bottom. So that's how it fits into the graph where it has the engine in the middle. Yep, and both of these two, when the heat is going in and out, it stays at a constant temperature, so it's expanding or contracting depending on what it is. Yeah, and that's about it. Have to admit, I've always kind of liked the idea of being a train conductor. Something I've always kind of wanted to try. Maybe when I retire, I'll go and join one of those clubs. Where you do that? Fun. I know a lot about thermodynamics. I could give them some hand. I gotta get these Doritos.